Hello, myself Mr. Shukdev Saha, Assistant Professor of ECE Department from Regent Education and Research Foundation Group of Institutions. Today I am going to deliver a lecture on code conversion. Code conversion is an important topic of digital electronics. So those who are belonging from ECE background or electrical engineering background or CSC background, that is very important for them. Okay, so first you have to know what is code. When we are talking about code conversion, you have to know about the codes. Then after you have to convert the codes from one code to another code, that is the code conversion. So you have a specific code and you have to convert it into the another code, right? So first of all, what you have to know, that is what is code. So about the definition, that is, it is the digital data is represented, stored and transmitted as group of binary bits, and this group is also called as binary code, and this binary code is represented by the number as well as alphanumeric letter, right? And the classification of the codes are two types. One is weighted code, another is non-weighted code. So what is weighted code? In weighted code, each digit position has a weight or value, right? The sum of all digits multiplied by a weight gives a total amount being represented. So each digit has a weight and you have to sum up the all digits with the weight. So BCD or 8421 is a type of weighted code. These are the examples of weighted code. 8421 is a type of weighted code where each digit position is assigned a specific weight. Clear? So weighted code is basically the code with the positional weight, right? Each position, each digit has some weight, and with the calculation of this weight you can calculate the overall amount of the digit. Okay, now go for the non-weighted code. Now what is non-weighted code? You can understand that is just opposite of the weighted code. In non-weighted code there is no positional weight, right? That is the main difference between the weighted code and non-weighted code. It has no positional weight. Each position within the binary number is not assigned a prefix value, right? And no specific position are assigned to bit position in non-weighted code. And there is two non-weighted codes are gray code and XS3 code. These are the example of non-weighted code, that is gray code and XS3 code. Now you have to know that is what is gray code and what is XS3 code, right? Now go to the next slide. Here we are talking about here the code conversion. So code conversion will be done with the help of code converters, right? The conversion will be done with the help of code converters, right? So there are several types of code converters I am discussing here, that is binary to gray code conversion, gray code to binary conversion, BCD to XS3 conversion and XS3 to BCD conversion. Okay, these are the four types of code converters we are discussing here. So first one is binary to gray code conversion. That is just I am saying that gray code is a non-weighted code, as the position of bits does not contain any weight, right? The gray code is a reflective digital code which has a special property that any two subsequent number codes differ by only 1 bit. So there is subsequent consecutive two numbers will be differ only by 1 bit. This is also known as unit distance code. That's why it is also known as unit distance code. So this is a special type of property. It has special type of property that gray code has. So this is the basic definition or basic idea of the gray code. And binary code we have already know 0 and 1, that is binary number. Next, how we can generate that is the binary to gray code, right? So you have the binary number and you want to convert this binary number into the gray code number. That is the conversion, right? So here the generation of 4-bit gray code can be calculated using this formula. So what is the formula? That is G1, that is the digit, that is G1, that is the MSB. G1 is equal to B1, right? G2 equal to B1 XOR B2. Here G3 is equal to B2 XOR B3 and G4 is equal to B3 XOR B4. These are the formula. Now you have to look at here, that is the most significant bit, that is I am discussing, that is the most significant bit that has the most weight of gray code is always equal to the MSB of the given binary number. Other bits of the output gray code can be obtained by XORing binary code at index and previous index. So here I am doing that is MSB of gray code, that is G1, MSB of binary code, that is binary code, that is B1. So G1 equal to B1. Okay. And the binary to gray code conversion can be done by using XORing logic gate. You have to use XOR gate, right? A 4-bit binary code converter is shown above, and the input is binary code and output is equivalent gray code. So input here we are considering input as binary code and output as gray code. Look at here, that is this one, this is a table, this is very important table, you have to convert it into the gray code. Look at this, that is 4-bit in input section. In input section there is 4-bit binary number, that is B1, B2, B3, B4. 4-bit gray code number, that is G1, G2, B3, G1, G2, G3, G4. Okay. So look at here, I am just saying that B1, that is the MSB of the binary number, is equal to the G1, that is MSB of the gray code number. So look at this B1 number, that is these all are the same 0 0 0 0 0 0, and here also G1 are the same numbers. Then after you are getting, that is G2. Look at this formula. Here the formula G2 is equal to, what is the formula? That is B1 XOR B2. G2 is equal to B1 XOR B2. Okay. So B1 and B2 you have to apply the XOR formula, you are getting G2. Then G3 equal to B2 XOR B3, and the last one, that is G4 equal to B3 XOR B4. Take an example, that is take the first row. that is G2, that is G2 equal to, for first row it is 0. How it is 0? That is B1 is equal to 0, B2 equal to 0. So 0 XOR 0, that is obviously 0. Okay. When B1 and B2 differ, only that time we are getting the output 1. We know the XOR application. What is the output of the XOR gate? That is when both the input are same, that is 0 0 or 1 1, the output will be 0. And when it is differing from each other, that is it is 0 1 or 1 0, output will be 1. Okay. So following this logic, you have to find out the 4-bit gray codes. So 4-bit binary numbers are the input section and 4-bit gray code number are the output section. This is how we can find out the output, and here that is the circuit for the binary to gray code conversion. Look at this circuit. As we are discussing, that is binary bit B1, that is binary to gray code conversion, B1 is equal to G1. So just short circuit this line, you can see that is the first line, that is B1 G1. Next we are getting G2 at the output. So what is the connection? That is B1 XOR B2. So B1 XOR B2, we are implemented here a XOR gate. So this is XOR gate 1, suppose B1 XOR B2, that is G2. Next G3. What is G3? That is B2 XOR B3. So this is the second XOR gate, and the third XOR gate, that is B3 XOR B4, that is G4. Okay. So this is the binary to gray code converter circuit through which we can easily find out, easily calculate the binary numbers from a simple, we can easily find out the gray code number from a simple binary number. Okay. So this is the first conversion. Now next one, that is gray code to the binary code, that is the vice versa. I am discussing binary to gray code. Here we are discussing the gray code to binary number. Okay. So here in this case B1 and G1 will be same. Look at this formula, that is B1 equal to G1 and B2 equal to G2 XOR B1, B3 equal to G3 XOR B2 and B4 equal to G4 XOR B3. That is the formula that is through you can calculate the binary numbers. So here just opposite of the case binary to gray code, here we want binary number from the gray code number. So which one is the input section? That is gray code number is in the input. So input is gray code and output is its equivalent binary code. Okay. So and these are the formula associated with that. Go to the next slide, that are the explanation of the previous slide, that is I am discussing, that is the MSB of the binary code is similar to the MSB of the gray code, that is here simply B1 equal to G1. To get next bit, use the XORing operation among the MSB of binary to the next bit of the gray code. And similarly, to get the third bit, it uses XORing operation among the second bit of to the third MSB of the gray code, and so on. So this is the ongoing process. As you have the bit, you have to go through. Okay. Next slide. This is the circuit. This is the circuit diagram of the gray code to the binary code conversion. This is obviously 4 bit, G1, G2, G3, G4. These 4 bits are the input bits, that is the gray code. So here I am saying, look at the G1 B1, that is B1 equal to G1, that is G1 input is directly connected to the B1 output, okay, and B2 equal to G2 XOR B1. So B1 is just connected with the G2 here with the help of XOR gate. So we are getting B2, and this is B3 equal to G3 XOR B2 and B4 equal to G4 XOR B3. Okay. So this is the 4-bit gray code to binary code conversion table. Look at this table. Just I am saying for the circuit, same here, G1, G2, G3, G4, that is this one, and output is from this B1, B2, B3, B4, and this is the table, that is the conversion table. Okay. Next one is BCD to XS3 code. Okay, BCD to XS3 code. So XS3 code, first you have to know what is XS3 code and what is BCD code. BCD means binary coded decimal number. Okay, binary coded decimal number means there is a difference between the binary number and BCD number is that each digit of a number should be converted into the binary number. Suppose you have a decimal number 11. So here 1 1, each decimal number should be converted into the binary number, that is 1 1 means 1, that is 0 0 1, and also 1, that is 0 0 0 1. So that is the BCD number, that means binary coded decimal. Okay, clear? And XS3 means that is a very simple code, that is XS3, you have to add 3 plus 3 with the binary number, that is the XS3 number, right? When it is suppose 0 0 0 0, suppose 0 decimal number, so what is the binary number? That is 0 0 0 0, right? Now 0 0 0 0, that is the 0 decimal number and binary number is 0 0 0 0. What is the XS3 code? That is 0 0 1 1, that is plus 3, you have to add plus 3. Simple. When it is, suppose it is 8, right? So you have to add 3, that is 11, that is you have to convert it into the binary number, that is the XS3, that means XS3 you have to add. So look at here, look at this table, you can understand better. So here look, that is decimal 0, this is the first one, input section is BCD number and output section is XS3 code number. So B3, B2, B1, B0, E3, E2, E1, E0, right? So here the decimal number is 0, that means the corresponding binary number or BCD number is 0 0 0 0, right? Then what I am saying, that is XS3 number is just plus 3 of the binary number or BCD number, that means you have to add plus 3, then 0 plus 3, that is 3. So what will be the XS3 number? 0 0 1 1. Look at the first row, that is E3 is equal to 0, E2 is equal to 0, E1 equal to 1 and E0 equal to 1. Next 1, that is 0 0 0 1. The corresponding number will be 4, that is 1 plus 3, that is 4. So what will be the conversion? That is 0 1 0 0. Look at the second row, 0 1 0 0. Okay. Next that is 2 plus 3, that is 5, that is BCD number is 0 0 1 0, that is representing 2, and the corresponding XS3 is 0 1 0 1, that is 5. So in this way you can find out the XS3 code numbers for the other BCD numbers. BCD number up to 9. Why it is up to 9? Because after 9 it is 10, that means 1 0. So you have to convert 1 to the binary number, 0 to the binary number, then bit number will be changed, then bit number will be 5. But here we are doing with the 4-bit BCD number. So you have to consider from 0 to 9, from 10 onwards. For 10 to 15 will be don't care. I think you know about don't care. If you don't know, I will discuss later. Okay. So here look at this, that is, this is the 9-bit, last one, that is 9, decimal number 9, that is 1001, that is 9. So what is the XS3 code? 9 plus 3, that is 12. XS3 code is 1100, that is 12. Clear? So you have to first build the table, right? Now look at this K-map. I think all of you know about the K-map. That is the fundamental thing of the digital electronics. You should know about the K-map, otherwise you cannot simplify the logical expressions. So look at there, you have to find out the K-map for E3, E2, E1, E0, right? And the input is B3, B2, B1, B0. Okay. So look at very carefully, this is the K-map for BCD to XS3 code converter, right? So first one, that is for E3. Look at the first K-map, extremely left side, that is B3, B2, B1, B0, these are the inputs, and the corresponding value is 00, 01, 11, 10. Here also B3, B0, for B3, B0 it is 00, 01, 11, 10. So you have to first write down the positional weight of the each boxes. There is 16 number of boxes. Why it is 16 number of boxes? Because it is 4-bit, that is 2 to the power n, that is 2 to the power 4 means 16. So here 16 number of boxes, and the positional weight is from 0 to 15. So write down the positional weight: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So in a manner you have to write down the positional weight. Next you have to put the don't care. Just I am saying that don't care is also a fundamental thing of K-map. Don't care means we do not care, right? Don't care means we do not care whether it is 1 or 0. We don't know also whether it is 1 or 0. So when we require 1 against a don't care, that is denoted as x, we consider as 1, right? So put the value from 10 to 15 as don't care. Look at here, look at the K-map, that is, it is from 10 to 15, all the values are the don't care. Why it is don't care? Because look at this table, after 9 we do not have any data. So if you do not have any input data, how you can get the output? You don't have the output. So output may be 1 or 0, right? So output may be 1 or 0. So you can classify, you can define it as a don't care. So first put from 10 to 15 as don't care. Then you have to put the values where it is 1. So for E3, look at the position where it is 1, 5, 6, 7, 8, 9. These position are 1, right? This is, look at this position, that is 5, 6, 7, 8, 9. These position are 1. Now just pairing, I think you can do this. That is the pairing process, K-map process. We have already discussed in the previous lecture. So I am not illustrating here. So from here we are getting the values, these, that is E3 is equal to B3 plus B2 B0 plus B2 B1. And here for also we are getting K-map for E2, E1 and E0, right? And from this K-map we are getting the logical expression, right? So now just this is the circuit diagram for BCD to XS3 code converter, and this is the circuit diagram. So look at here, B3, B2, B1, B0, and this is the XS3 code E0, E1, E2, E3. E0 equal to B1 bar. So it is connected with the NOT gate, right? Now E1, what is the value of E1? That is E1 equal to B1 X naught B0. That is here, look at here, that is the X naught gate. So this is how we are getting the BCD to XS3 code converter, and you can easily convert a BCD number into the XS3 code, right? Now going to the next one, that is the XS through BCD, XS3 to the BCD code converter. That is just opposite of the previous one, you can understand. If you know the XS3 number, if you know the BCD number, you can easily convert. The process of converting is just the opposite process of the converting to BCD to XS3, and BCD number can be calculated by substituting 3, that is 0011 from each 4 digit, that is XS3. Look at here, look at this position, 1 minute, that is it starts with 0011. Why it starts with 0011? Because XS3 012 is absent for XS3, right? Because it will start from XS3, that is 0 plus 3, so that is 0011. So if XS3 is equal to 0011, that means 3. What will be the BCD number? Obviously 0000. Look at the first row, it is 0000. Okay. Next 1 plus 3, it is obviously 4. So it is 0100. That means E3 is equal to 0, E2 1, E1 0, E0 0. The corresponding BCD number will be 0001. Okay. Next 2, that is 2 plus 3, it is 5, 0101, right? The corresponding BCD number will be 0010. So in this same method you have to find out up to 9, as BCD number is up to 9. After that it will be the 5 bit, right? So 9 plus 3, it is 12. So XS3 number is 1100. Look at the last row, that is BCD number is 1001. Now go to the next slide, that is the K-map for XS3 to BCD code converter. So here we have to find out, that is B0, B1, B2, B3. Same thing, if you know how to find out the minimized expression with the help of K-map, you can easily do it. that is the input section here, E3, E2, look at the K map, E3, E2, E1, E0. These are the input, and output for 4 outputs, for 4 logical expressions, you have to do 4 K maps. That is B0 equal to E0 dashed, B1 equal to E1 XOR E0, and B2 and B3 here. That is the logical expression expressed here. And this is the circuit diagram that I am discussing here, that is the XS3 code to BCD converter, that is input section. Look at here students, that is E3, E2, E1, E0, these are the inputs, right, and BCD code at the output section. So B0 is equal to E0 bar, right, B1 is XOR gate of E2 and E0, E2 and E1, and B2 and B3 have the logical expression we are getting from the K map. Accordingly, you have to do the converter circuit, design the converter circuits. So this is how you can design a XS3 to BCD code converter. So these are the end of the lecture. So from today's lecture, we know that how to convert the codes, that is basically how to convert XS3 code to the BCD code, BCD code to the XS3 code, binary to the gray code to the binary code. So here we are basically learn about the codes, what are the codes, basic idea of the code, and the code converter circuits. Here the most important, that is the code converter circuits, how we can convert and how we can get the different codes from the another code. So I think you have learned the code conversion techniques. Thank you students. I have stopped here my lecture. Thank you.